In this example, we have a car taking a curve. We know the radius of the curve is 15.1 meters. We know the coefficient of friction between the ground and the car is 0.34. And we're asking what's the maximum speed the car can have as it takes the curve. Now, our everyday experience tells us that there is some maximum speed at which the car can take the curve. If the car moves too quickly, it will slide and not be able to make the turn. Why is that? Well, in order to make a curve, you have to have centripetal force. What's supplying the centripetal force in this case? Well, it's the friction between the car and the road. The friction between the car and the road provides a centripetal force pushing inward to the center of the circle, and that allows the car to take the curve. So the maximum speed is determined by the centripetal force, which is in fact the friction. So in other words, the friction between the car and the road is what determines how fast the car can travel around the curve. Well, if friction plays such an important role, we better try and figure out what its value is, right? We have an equation for the frictional force. It's mu times the normal force. While the car's on the road, its weight is pulling down. In order to keep the car from falling through the road pushes back with a normal force. So the magnitude of the normal force is the same as the weight of the car. So we could take normal force and replace it with m times g. So the frictional force is mu, which we already know, 0.34, times m times g, which we also know, 9.8 meters per second squared. If we deal with both of the numbers in this problem, 0.34 times 9.8, we find that friction is 3.3 meters per second squared times m. Unfortunately, we don't know m, so we don't exactly have a number for the frictional force. However, that's not stopped us before. We often end up with equations with two unknowns. What do we do in those cases? Well, we look for another equation. Well, we do have another equation here. We also know that centripetal force equals mv squared over r. Now, what's the centripetal force? We don't have a number for it, but we have an expression. Because remember, the centripetal force is the frictional force. So whatever equation we have for frictional force, we can substitute for centripetal force. So the centripetal force is 3.3 meters per second squared times m. We don't know the mass, we don't know the speed, but we do know the radius. The radius is given, it's 15.1 meters. So we have this equation, 3.3 meters per second squared times mass equals mass times v squared over 15.1 meters. Now look at what happens. The mass cancels. I have m on the left-hand side of the equation and m on the right-hand side of the equation. M cancels. And actually, if you think about it, it's really nice that m cancels. Since m cancels here, what that tells us is the maximum speed at which a car can take a curve is not affected by the mass of the car. A tiny little Volkswagen and a big 18-wheel truck essentially have the same maximum speed around a curve, because the maximum speed around a curve does not depend on the mass. Since mass cancels, we have only one unknown, v squared. We can solve for it by multiplying both sides by 15.1 meters. So v squared is 3.3 meters per second squared times 15.1 meters. To finish the problem then, I multiply the numbers and the units together and then take the square root of both sides, and I find that the speed is 7.1 meters per second. So that means that any car, this car, any car, can take this curve with a maximum speed of 7.1 meters per second. Anything less than that is fine, but anything more than that will cause the car to skid off of the curve, because the centripetal force will not be great enough to hold it in circular motion.